Hello everyone and welcome to today's webinar. For those of you who are new to the webinars, just a few notes. Audio is provided over the GoToWebinar app, which is over the internet, so please enable your speaker in all places. The application has muted your microphone, so I cannot hear you. However, there is a questions tool at the right side of your screen in the app. You can use this at any time to ask me a question. I will take a look periodically and read the questions and answer them if we have time. If not, I will send you your answers directly after the webinar. Today, we are going to do an overview of the safety lifecycle and how we address the tasks of the safety lifecycle with exSILentia. And I'm doing this mostly because we usually focus on one task at a time, whether it be from a consulting point of view or within the software. We like to do a deep dive into each task, but we're going to take a simple sample problem in this case and just take a look at how the data flows from one task to the next. Before we dive in, I should introduce myself. My name is Kate Hildenbrandt. I am product manager for exSILentia at exida, and so I'm responsible for the strategy, roadmap, and feature definition for our exSILentia software. I'm also focused on providing training and software support to our customers. For that reason, I have my email address right here at the bottom, khildenbrandt@exida.com. Please feel free to send any questions you have on our software tools to me or about what we do at exida at large. I'm going to give you a little overview of what we do at exida. We do have three main functional groups within the company. Obviously, we make enterprise tools. They address functional safety, alarm management, and cybersecurity, and that's what my group does. I'm in the product group. We also have consulting services that address the same thing. So functional safety, cybersecurity, alarm management. So everything you can do with our software, you could also ask us to bring one of our experts in and help you along with that. Additionally, we do certification for devices used across the industry and safety instrumented systems, and we also certify personnel. So if you're familiar with the CFSE or CFSP programs, we are also responsible for that. So if you have any additional questions on what we do at exida, hopefully between these three groups, we can help you with any of your safety needs. We do have locations around the world. I am personally located right outside Philadelphia, Pennsylvania in the US, but if you are located elsewhere, hopefully you can see an office near you. We also do consulting services internationally, again, that address functional safety, alarm management, cybersecurity. So we're going to start with a high-level overview of the safety lifecycle. And this is usually how you will see the safety lifecycle depicted. And it's basically almost a top-down list, starting with your process design. You're going to basically break it up into smaller pieces and analyze it for any inherent risk in your process. If you have some high-risk scenarios that could occur within your process, you're going to allocate safeguards and safety functions, independent protection layers against those hazard scenarios. Then a safety requirement specification will be written so that you can let the design team know exactly what they need to design. Then your safety instrumented system is designed, and you're developing your other means of risk reduction that aren't safety instrumented functions. Finally, these are implemented. You're going to install, you're going to do testing, factory testing and site testing to make sure that these are implemented correctly. And then you're going to put your process online. When your process is online, you need to operate and maintain. So you need to do proof testing to make sure your safety instrumented system is functional, and as well as recording of device failures, routine maintenance, recording of the process demands. If any modification is needed, you'll obviously have to address that, and that's more of an iterative process as your plant is online. And then finally, at the end of the life of the plant, you're going to do decommissioning. Now, the way this looks is specifically from the standard, IEC 61511, and again, it looks like a top-down list. And it's obviously providing a method to analyze your system for inherent risk and then implement and maintain a safety system from project scope to decommissioning. But what it doesn't show is that from a data flow perspective, this is more of a cycle, which again is why we call it a safety life cycle. So we like to look at it as a cycle. And the reason we want to highlight this is because the information from each task will fuel or jumpstart the next task. So for instance, if you're doing a process hazard analysis, you're obviously taking your system, again, dividing it into units and nodes, and analyzing any challenges to your process parameters. You'll look at the causes of those challenges, the consequences, and the safeguards. In the LOPA, those same causes are going to be your initiating events, and those same safeguards are going to be your independent protection layers. Any independent protection layers that happen to be a safety instrumented function are going to undergo SIL selection, so you can determine the safety integrity requirements that you need to design to for that SIF. And then for each SIF, there is a large list of requirements in the standard outlined for you to document in the SRS, the Safety Requirement Specification. This is meant to communicate all of the important information from the analysis to your design team. The design team will receive that and do the conceptual design and SIL verification. So here you're choosing your devices, you're modeling your SIF architecture, and you're putting together your proof test strategy. What are your proof test intervals? What's the proof test coverage based on the proof test procedure? While you're doing this conceptual design, you're going to want to take into account the cost of what you're implementing. So is redundancy more optimal than doing proof tests often, or vice versa? And so we do have a life cycle cost element to our software where you can optimize your SIF design based on obviously meeting your safety integrity requirements, but also optimizing the cost of implementing your safety instrumented system. Once your conceptual design is set in stone, you're going to write another safety requirement specification. Here we have a module called Design SRS where you're communicating your conceptual design for implementation. This is a little different from the analysis one because some of those are intended or requirements, and now you're communicating exactly how it should be implemented. Once your plan is online, you're going to have to do proof tests, and these proof test procedures are going to depend on the devices that you chose during a SIL verification. So we do have a proof test generator that will allow you to create your proof test procedures based on the devices chosen, as well as the intervals and the proof test coverage. In the PHA and the LOPA, you might be dealing with some alarms as safeguards and then independent protection layers. This information can feed into our alarm rationalization tool, SIL Alarm, which is going to allow you to prioritize, classify the different alarms and how you want them to be implemented in your safety system so that the operator has a chance to effectively respond to the alarms. And you want to know if they are in fact IPLs and if they've been given some risk reduction factor that will help during the rationalization process. So that's something that, again, you can leverage your analysis to jumpstart your alarm rationalization. Finally, in the O&M phase, you want to keep track of your plant performance, your safety instrumented system performance. So this means keeping up with your proof testing, your routine maintenance your devices require, as well as any device failures or demands on the process. All of this information over a number of operating hours is going to give you plant actuals that you can use to either validate your analysis, validate your design, or feed new analysis and design for a greenfield system. And so when you look at the transfer of data from one phase to another, you can see that this is truly a cycle. And we are hoping that we can help you streamline your work process so that you're leveraging the information from one task to jumpstart the next. Now, in this webinar, I'm going to focus on phase 1 analysis, and I'm going to walk you through a few slides that show you exactly how we would implement this within a tool, and then later on, I'm going to dive into the tool with a simple process example and show you live how I would do it. So again, we're dealing with the analysis portion. We already saw the safety life cycle. The analysis will include your PHA, so this is hazard and risk assessment, and then the LOPA, your allocation of safety functions to protection layers. It will address SIL selection, whether it be based on LOPA, risk graph, or risk matrix, or whatever your SIL selection method is, and then documentation of your safety requirements in the SRS to hand off to the design team. So we want to highlight exactly what we're doing here to summarize it. Basically, in the PHA, you're brainstorming all possible hazards in your conceptual design. So as I said, you're breaking down your system into smaller pieces, units, nodes, and for each node, you're going to have a number of deviations, which are challenges to your process parameters. For high-risk scenarios, you want to identify protection layers against these hazards. So that's done in your layer of protection analysis. For IPLs that are SIFs, you want to determine the integrity requirements for those SIFs so that the design team knows what to design to. So that's done in your SIL selection. And then you want to document all SIF design requirements for implementation. You want to be compliant with IEC 61511, so you want to address each requirement that it lists as important to include in this specification. And so that's your safety requirement specification task. So I'm going to walk you through a high-level look at how you would do this within the tool. You're going to start with your PHA, and in this example, and I don't want to get too into the details because I'm going to do that in a little bit, but you have a unit which is a chemical batch reactor unit, and you have a node which is a reactor. For a reactor, you can see there are 26 deviations. These are challenges to your process parameters that guide you to say, what could go wrong in my process? And so you want to go through these each methodically and take a look, brainstorm what could go wrong. Then you want to document the cause, which is answering the question, why did it go wrong? In the process, what caused this deviation to the process parameter? Then you want to document how bad is it? What is the consequence of this happening? For the cause, you're focusing on how it could go wrong and how likely it is. For the consequence, you're focusing on how bad is it? So what's the severity? What is the impact that this could have? Here you can see we have a safety consequence, and in that case, you might have to basically determine, could this cause lost time? Could this cause an injury? Could this possibly cause fatalities on-site or off-site? And that's the sort of analysis you're going through. If you have a high likelihood and a high severity, you're going to have a high resulting risk, and you're going to want to analyze this further. We also have a business consequence. So in this case, that's loss of usable product. This means that it might cost your company some money, whether it be that you didn't produce as much from your process as you wanted, or perhaps you damage some equipment that you have to replace. So that would be a business consequence. And in that case, the severity might depend on exactly how much you're losing. We also like to focus on environmental consequences. So we want our process to be easy on the environment. And if you have a consequence that is really affecting the environment, it might be, you know, how bad have you contaminated the environment, and some of your high risk scenarios will be associated with that. If your consequence and your cause output a high risk, you're going to want to document safeguards. And this answers the question, how can we protect against this? Is there anything already built into our process that will protect against this hazard scenario? And these are often alarms with operator response. You might have pressure relief devices. You might have procedures. You might have physical security, like a dike for a environmental spill. You might do training for your operators or anybody involved to implement as a safeguard against this hazard. Once the safeguard is documented, you're going to have a resulting likelihood. Now that we've considered these safeguards are in place, how likely is it that this would actually occur? And that will output a risk with the safeguard. So what is your resulting risk after the safeguards have been taken into account? At this point, you've taken a look at what your process has, and you can then document recommendations. How can we learn more? If it seems like we're really not sufficient in our safeguards, what can we do to determine what more could be done? These can be evaluations, these can be calculations. You might want to write extra procedures, things like this. So you want to document recommendations, assign them to somebody, give them due dates, and address them as soon as possible. Finally, you want to determine if this is a high enough risk scenario. Do you want to analyze it further in the LOPA? Not everything's going to be high risk, and so you can maybe stop at the PHA, but certainly some things you're going to need to do layer of protection analysis. And if it is, you have to define a hazard scenario. So your hazard scenario might just summarize the cause-consequence pair, or it might summarize something that could, a hazard that could be caused by multiple cause-consequence pairs. And so this would allow you to analyze either one initiating event per hazard scenario or multiple initiating events per hazard scenario. This depends on exactly how you want to do your analysis, but the tool is capable of both. Once you get to your layer of protection analysis, it's going to be organized by hazard scenario. And the initiating event here is your cause from the PHA. So you see the exact same cause. Here you're going to give it an actual frequency. So this can come from the database built within the tool or your own database, perhaps simply experience. You can type it directly in. Your safeguards from the PHA become IPLs in the LOPA. And so you want to order them in the order you expect them to act against the hazard. So your alarms might be first, and then maybe a safety instrumented function, and then maybe a relief device. Depending on your IPLs, you get to determine if they are, if your safeguards are truly independent, and we can talk about that in a little bit. In this case, as you're doing your LOPA calculation, you want your actual frequency to match your target frequency. And if it doesn't, you're going to have a resulting risk reduction factor. You can have this risk reduction factor just apply to the hazard scenario at large, or you can choose to apply that risk reduction factor to your instrumented protective function or your SIF. So we use the term IPF, meaning we don't know if the risk reduction factor is above 10 or would qualify as a SIF, but certainly once you do this calculation, you can determine what the risk reduction factor is for your SIF. And in this case, you see up above that the target frequency and the actual frequency are equal, and that risk reduction factor says NA because it's now applied to the SIF. Here you can see the calculated risk reduction factor in the SIF view. So you see that your probability of failure is 0.1 and your risk reduction factor is 10. So this is one way you can do SIL selection based upon the LOPA. We can also do it with risk graph and risk matrix, which I can give you a look at in the tool, but this is how we would do it here. And then for those SIFs that result from the LOPA, you have to fill out a safety requirement specification. And within exSILentia, this is essentially a template that ensures that you're addressing each of the requirements in IEC 61511 to be compliant with that standard and to effectively communicate the requirements that you've determined in analysis and hand that off to the design team so that they can design a truly safe safety instrumented system. So that is a really quick overview of the different tasks in the analysis phase of the safety lifecycle. And I want to take a deeper dive by opening the tool and basically walking you through each of these steps. And to do this, we're going to need a practical example. So this is meant to be pretty simple so that we can highlight exactly how the data moves from task to task, how this can be done within the tool. So we have here a batch reactor, and I said it was simple. It looks like a lot's going on here. I'm going to use my spotlight to show you a couple of things that are going on with this batch reactor. And again, this is just a sample problem that we'll use here. So we have feed A coming into the reactor and feed B. They're both being used. You have an agitator here. A couple things I want to highlight. We have a few pressure transmitters here. If the reaction has too high a pressure, this pressure transmitter will cause this pressure control valve to vent pressure to an incinerator. If for some reason that fails, this pressure transmitter will basically, it's an instrumented protective function interlock that will do a few things. You're going to open this valve XV500 to dump the reactor contents into a quench tank, which is much bigger, which will effectively relieve the pressure and make sure that the reactor itself does not rupture. It's also going to close the valve that allows feed B to enter the reactor, and it seems as though feed B is the ingredient that would cause the high pressure and perhaps an exothermic reaction. It's closing a valve that brings hot water into the reactor jacket, and it's opening the valve that allows the chilled water in. So a few things are happening when high pressure occurs. You can see we also have interlocks for high temperature, which again are going to allow chilled water in and allow and not allow hot water in by closing this valve. If your optimal temperature doesn't want to go too low either, you can do the opposite. And we have a few flow controls and a level control here as well. For the sake of simplicity, I want to focus on that high pressure scenario. And so when we're doing our analysis, and I'm gonna, obviously show this to you now, when we're doing our analysis, it seems that the only way that we can have high pressure in this reactor is if this control valve fails, right? So we would consider that a failure of the BPCS. So if pressure gets too high here and this control valve fails, it can't vent to this incinerator. So what are we relying on to mitigate this hazard? Well, we have this other pressure transmitter, and it's going to ensure that this valve opens and dumps into the quench tank. Now I mentioned that a couple other things happen. Interlock 3 is also going to let the cold water in and make the hot water stop in the jacket, and it's going to stop that feed B. But the true function that makes sure that the hazard is not going to occur is just that jumping into the quench tank. So that is basically our safety instrumented function. There is a high pressure alarm and a high pressure alarm. So our normal operating pressure is 10 psig. In this example, our high pressure alarm goes off at 15. We have another high pressure alarm at 20 psig, and then our interlock is going to trip at 20 psig. Finally, we have a rupture disk here that's going to lift at 60 psig. So we you know, for a few reasons might not want to vent to air, but it's our final safeguard against a true high pressure hazard happening. So this is going to be the basis for me to walk you through the analysis portion of the safety life cycle. So now that we've gone through that, I'm going to open exSILentia. Okay, so you should see exSILentia on your screen. And a couple things I want to go through real quick before we jump into the PHA. You can configure a few things in exSILentia that will allow you to basically guide you through the PHA and some of the other analysis. When I say configure, it means that you can do this yourself. So if you have a license to the tool, these changes can be made without help from us, without help from the software team. Just with a license, you can do these yourself. So a few things that are helpful for reference: we have different plant types and different process types. Any place that you see these plus or minus buttons, you can delete anything we have here in the default project. You can add anything, and you can change the order. Depending on your standards that you have throughout your company, if this is always consistent, you can do it once and always bring this project configuration in. If you're working with different companies to do this analysis, you can obviously change this as needed to suit the application and the company that you're working with. We also have node types, and for each node type, and I'm going to pick Reactor here because that's what we're working with, we have default deviations. So for a Reactor, you can see these deviations that we feel that you should address during the PHA. You can always add more, and you could always take away. But this should help you when you're going through defining your nodes. You pick the node type, and it's going to automatically fill in these default deviations and guide you through the analysis. The other thing I want to highlight before we start is the risk configuration. And this is going to help you to define the different severity categories that you want to analyze in the PHA, so and your LOPA. So here you see our default always has business, environment, and safety. But you can, again, if you want to add corporate image, if you want to add personnel versus, public safety, things like that, you can adjust this as needed. We also have severity levels, and here we can define the tolerable frequency for each level. You can input descriptions here in the severity matrix for each of the severity categories according to the level. And this is simply text, but it's good reference. You can come in here and change this as needed. But obviously for business, we have negligible impact to above 250 million. For environmental, we have negligible to permanent damage to environment, rendering land unusable. and for safety, it's negligible to on and off-site fatalities. So this is default with the project, and helps you, again, while you're doing your process hazard analysis. We have the same for likelihood, so you could have multiple likelihood categories if you like. Some people like to have one for qualitative and one for quantitative frequency. So depending on how you like to do it, you could see there's also a likelihood matrix. We have frequencies in here, but if you'd also like to add something that has qualitative descriptions, you could do that as well. And this results in our risk matrix. This is completely customizable, so you can change the colors, you can change the axes, you can basically do whatever you need to configure this to fit the corporate criteria that you're working towards. So again, before we walk through our process hazard analysis, I just wanted to show you that. But let's jump in. In this case, I already have a sample in here. So I have my batch reactor unit already defined. And for the unit, I have the plant type. We specified it as chemical. The process type is polymers. The process mode is batch. And then I have a process description here. So, we went through the PNID, but essentially the batch reactor makes product from mixing A and B in the presence of a catalyst that is contained in B. The reaction is highly exothermic once it is initiated, but requires sufficient temperature for initiation to begin. So you get the idea. You can put a detailed process description in here. Then you can define your nodes. So here we have reactor 1. I'm going to add a second reactor so that we can start fresh. And I'm going to name this reactor 2. And in this case, I could put in an intention for the reactor and I can put in comments. For the sake of simplicity, I'm going to jump to the node type, which is going to be simply reactor. Here I can link any references from the library that I feel like linking. But this is basically how I define my node type. Here I can use the navigation tree to expand the node. And as we talked about earlier, these deviations auto-populate based on my node type. So because it's a reactor, we have these 26 deviations that we can go through to do our process hazard analysis. As always, you can add or delete deviations as needed. One thing I think it's helpful to know is once you're done analyzing your deviation, you can hit complete. Or say you come to a deviation where you didn't find any causes or consequences to document, you can simply hit no issues. It's going to add a symbol there. And I think this is sometimes preferable to just deleting the deviation, because what it shows is that you've considered it and there's nothing that you can find that could occur with this deviation. If you delete it, perhaps down the road someone else reviews it and says, how could you forget to analyze this? So that's one way you could do that. In this case, we know there is some hazard associated with high pressure. So let's dive into that. So I've selected my deviation and I'm just going to add a cause here. And we talked about how in this case, the only way you're going to really have a high pressure hazard scenario within the reactor is if there is a failure of the BPCS control loop. So our pressure control valve breaks, we can't vent to that incinerator. So I'm going to document that here. And in this case, I'm going to then select a likelihood from our risk configuration. We'll say this is pretty likely. Once we've documented the cause, we want to look at any potential consequences. So I'm just going to select the Add Consequence button. In this case, we could have, let's say, a reactor rupture that could harm people in the surrounding area. So I will document that here. And you can see that the categories, business, environmental, and safety, can be analyzed all at the same time. So they're automatically highlighted here. In this case, I would like to just do one at a time. So I'm going to deselect business and environmental, and you see that they completely disappeared. Let's say I say, oh no, I want environmental back. You just come into the settings and uncheck this hide non-applicable severity categories. So I can get them back and I can say, hey, this applies too. And then if I want to hide again, I can do that. In this case, I do only want to look at safety for this consequence. And just like we chose the likelihood, we can choose the severity. We'll say this is a high severity consequence because we could have actually, I think 5 was on-site fatalities. I can add any comments here if needed. So I've documented my consequence. I can go on here and add some safeguards against it. And if you remember the process, we had a high pressure alarm and a high pressure alarm. So we'll document those first. You can see that it's autofilling here to say you already have some high pressure alarms in your PHA, but this is a different alarm. So I'm going to just continue to enter this new one. And for each safeguard, you can specify a category. So this is alarm with operator intervention. We assume each safeguard of alarm type is going to have an operator response. And here you see the CD button, and this is something I can expand to show custom data. So fields can be defined within exSILentia in the project configuration for anything that you think you might want to add more information to. In this case, we know that alarms often need to be rationalized and that you might want to document this right here if you have the alarm information at your fingertips. You could also document this detail for your alarms later. This particular custom data is default with the exida project file. You can delete it if you want. You could create any custom data that you want to apply to the different safeguard types. And then, of course, any comments can be added here as well. So let's go on and put in our high pressure alarm. And this is going to look a lot the same. Finally, we have our interlocks. So we know that when PT 501 senses high pressure, it's going to then tell the logic solver to open XV500, which is going to dump the reactor contents into a quench tank. So let's document that here. We're going to call it an IPF right now because we're not sure what risk reduction will be attributed to this safeguard. So instead of calling it a SIF, we're going to stick with IPF until we've done our LOPA calculation. And this is PT 501 senses high pressure, opens XV 500. In this case, I'm going to give it a tag. And again, that category for now is going to be IPF for instrumented protective function. Our last safeguard is that rupture disk. It's going to lift at 60 psig, I believe, and vent to air. It's PSE 500 in our sample. And here our category is rupture disk. So these are the safeguards that we have specific to the high pressure hazard scenario or cause consequence pair. Now that we've taken these into account, we want to now document what the likelihood is with these safeguards in place. And that is going to be obviously have an impact on the likelihood, and the resulting risk is 16, a little less than what we had over here, which was 20. Still high enough risk to continue to analyze in the layer of protection analysis. Now, I want to go back and say, okay, what if we have another consequence? And we'll do this quickly, but let's say that runaway reaction from decomposition causes loss of usable product. And in this case, we'll say this is a business consequence, and we'll say that we're gonna lose a lot of money in this case. Our safeguards for the business consequence are going to match the safeguards for the safety consequence. And what we can do here is actually link these same safeguards from exSILentia's library. So exSILentia is actually, as you're documenting your analysis, saving all of the user input information into a library. So your causes, your consequences, safeguards, recommendations are all saved within the library and can be linked as you're going through your analysis. So I don't want to put in another pressure alarm if I already have custom data and everything filled in. So I can come in here and choose my specific safeguards and add them. You can see the different IDs and you can reorder these as needed. You can see the specific IDs match. So it's 10, 11, 12, 13. And what I want to show you is how this really helps to keep things consistent. So if I come in here and I say, oh, this isn't venting to air, this is venting to a safe location, you can see that that edited in both spots. If I want to say, hey, instead of PSE 500, this is actually PSE 555. That is changing in both spots. And so this is pretty helpful in keeping consistency and making sure that you're not making errors as you go through and change things. And it's also helpful because we can then link these specific safeguards to other places in the life cycle. Again, we want to pick a new likelihood with our safeguards in place, and we have a resulting risk. Finally, we want to document the any recommendations that go along with this. So let's say in this case, we want to evaluate the risk reduction associated with that instrumented protective function. And, you know, we know we want to analyze this in the LOPA, but, you know, you can put in any recommendation here. Maybe you're evaluating different procedures. Maybe you want to consider physical security. Maybe you want to do calculations. Maybe while you're doing your analysis, you realized your PNID is inaccurate, and so you want to go back and update and correct your drawings, anything like that. So you can add your recommendation, you can give it a category. In this case, we're going to perform an evaluation, and that'll be category eval. If you have team members defined in exSILentia, you can assign somebody this task, and I'm going to assign myself. You can add a due date. So I'm going to get this done in a week, let's hope. And then you can add a status. So in this case, it's open, but it's also assigned. The other statuses are ready for peer review. Is it approved and is it closed? These are things you can configure within the project configuration. So if you want to add to the categories, to the statuses, that's completely up to you. And in this case, we'll link that same recommendation to our second consequence. Finally, we know we want to analyze this in the LOPA. So we're going to say, yes, the LOPA is required, and we're going to define a hazard scenario. In this case, when I add the hazard scenario, it's going to automatically name it after the cause-consequence pair. And you can leave it that way, and what that will mean is that you are basically going to have one initiating event per hazard scenario. If you wanted to rename it, you could apply the same hazard scenarios to multiple cause-consequence pairs, and that's going to allow you to analyze multiple initiating events per hazard scenario. Everybody likes to do it a little bit differently, but the tool accommodates both. We're going to do the same thing here. And so we'll have two hazard scenarios for the different cause-consequence pairs. I do have another hazard scenario in my sample project, and that one, it does have two initiating events, so I can show that to you as well. So that's a quick overview of the PHA. We can move over to our LOPA sheet, and the first thing I want to point out is that our hazard scenarios are already listed here. And you can see my runaway reaction from decomposition has two initiating events. So this is one case where you can take both of them into account and see the impact on the IPLs. We're going to stick with one hazard scenario at a time. And the one I've selected is our safety. The reactor ruptures and potentially causes an injury or an on-site fatality. As you can see, my LOPA worksheet is blank. One thing you can do within the module is you can select this top button, and this is going to load all the data from the PHA for all the hazard scenarios at once. And that's really great when you're first starting out. However, I already have a hazard scenario I filled in information for. So instead, I'm going to choose the second button, which is to load the data from the PHA for just this hazard scenario. When I select the button, it's going to give me a warning that says, hey, if you've done any work here, this will overwrite it. And I say, yes, I haven't done any work, so I would like to apply this information. And right away, you can see everything that we just filled in the PHA is automatically filled in here. So our cause becomes our initiating event. That is our pressure control valve failing, cannot vent to the incinerator. And for this cause, I want to add a frequency. Now I can enter the frequency directly, or I can use the database that we have embedded in the tool. This is an exida database. We know that this is BPCS control loop failure, so I can simply select that. And on the side here, you see the references, assumptions, and comments that all contributed to coming up with this frequency. I can simply hit apply data, and those are easily found right here, assumptions, comments, and references. One thing I want to point out is that there is an exida database. You can also create a user-specific and project-specific database. If you already have data that you've been using for your LOPAs, you can simply put them into the tool just like this and select them just as I did from the exida database and apply them to your LOPA worksheet. You can also simply just enter it directly. Moving along to the IPLs, you can see these were our safeguards in the PHA. And you can also see that at this moment, we are looking at business, environmental, and safety all on one worksheet. we know that our hazard scenario only is addressing safety. So if you look up here, you can see our actual frequency, now that I put in the frequency for the initiating event, is not matching our target frequency at all. And we have a residual risk reduction factor of 10,000 here. But it's only the safety that we're looking at for this hazard scenario. So if I want to clean up the sheet a little bit, I can go over here, and instead of looking at multiple risk receptors, I can look at just one at a time. And I want this one to be safety for this case. Now it's cleaned up a little bit. So for my IPLs, I want to input a probability of failure. In this case, you're going to take a look at the safeguard by clicking the edit button. And you can see here the safeguard name. You can add a description. We have the tag already filled out as well as the category. You can, if you want to, document immediate consequence if this safeguard fails, and potential ultimate consequence if the hazard happens. You can link any references. So if you have a PNID and we do, that shows this specific alarm, you can link that there. But what I want to focus on is the LOPA section here. Here you can input the PFD directly, your probability of failure on demand, or your risk reduction factor directly. But you'll also notice there is a database button here. In this case, again, it's going to show you the database for different IPLs and their probability of failure on demand. And again, I want to point out that there is a user-specific and project-specific database that you can fill in yourself. In this case, I'm going to choose alarm layer of protection with operator response. So we're assuming the alarm is useless unless the operator does something. We're assuming both of those will occur. So here you see all of the backup information to go along with this piece of data, and you can apply the data there. Now, it's applied within the safeguard view. You can see now the PFD is 0.1 and my risk reduction factor is 10. But it's not applied in the sheet, and that's because you still have to determine, is this high pressure alarm going to guard against my initiating event? And is it independent? And the answer is yes. So I can simply double click the cross section there and apply my PFD. So here you're now seeing the actual frequency is updated and my risk reduction factor is decreasing. Moving along to the high pressure alarm, I could use the same piece of data, but in this case, it's not independent. And it's not independent because it probably relies on the same control system that my high pressure alarm relies on, or the same operator that my high pressure alarm relies on. If either of these fails, then both alarms fail. So I'm gonna leave my IPL here. I could delete it because it doesn't apply, but I want to show that, yes, I know I have a high pressure alarm. It doesn't apply. I'm going to leave it saying not applicable. Then I can move on to my rupture disk. In this case, again, I'm going to go straight to the database and I'm going to say that this is a pressure relief valve. And I am going to apply that data. Again, I'm going to say, yes, this obviously addresses my initiating event because it's going to relieve the pressure in the reactor once it lifts. And so I'm in good shape there. After I've taken into account the probability of failure of these two IPLs, I still have risk reduction left. Now, I don't know necessarily what the probability of failure is for my instrumented protective function. That's what is determined in SIL verification, but I do want to know what it needs to be. So I can just leave this risk reduction factor here for the entire scenario, or I could come in here and hit the calculate button. We know that this applies, and if we hit that calculate button, it's then taking that risk reduction factor and applying it to my instrumented protective function. So here you see a risk reduction factor of 11 has been associated with this particular IPL. And you can see the probability of failure on demand as well. In this case, because my risk reduction factor is above 10, I can hit that it is a SIF up here. And in that case, it will then automatically apply to select, to the SRS, to silver, design SRS, so on. So that's how you make sure that information is available. So now you see my target frequency is equal to my actual frequency, and so my LOPA analysis is done. I do want to point out that you can add enabling conditions by simply clicking this button. You can add your probability here, add any assumptions, comments, or references. And if you have application-specific enabling conditions, you can, again, fill out your own database here. We don't have any in the database because it is often application-specific. The same goes for conditional modifiers. So it works the same as the enabling conditions. And I also want to point out that you can add initiating events, additional IPLs here. If you did not do your PHA and exSILentia, you can simply start here with your LOPA. That is no problem at all. But you can see how easy it is to do when you've done your analysis in both tools. So now that we're done with this particular hazard scenario, we can do the same here quickly for this hazard scenario. We want to pull in the same information. We already have this initiating event frequency. We already have these. So done. We can move on now to select. So for each hazard scenario, you can select it from the left-hand side and see that the IPFs that are associated with that. Our analysis RRF is the RRF that is shown calculated from the LOPA. And you can say, yes, I want to use the analysis result in to design my conceptual design. You can also come in here and say, you know what, I want to bump this up just to be extra conservative. That's up to you, and that's why we leave it that way in the tool, to say you can just choose that analysis result yourself. I want to point out that you can do risk graph as well within the tool. So this is the risk graph from the risk configuration. You can choose your severity level, you can choose your likelihood level, and add any risk modifiers to get your target SIL. You can do the same with your risk matrix. And again, I just want to highlight that these are defined within your risk configuration. And this is completely configurable by you. But we're going to stick with the LOPA number because we did all of that work in the LOPA. Finally, you have your safety requirement specification. So here are my two SIFs. This is the one that we just worked with. And I wanna highlight what's pulled over into the safety requirement specification. Obviously, anything you've already filled in the library. Our demand rate is here, and this is dependent on the initiating events and any IPL that comes before the SIF in your LOPA. So this is taking all of that into account in the calculation. If your SIF is acting against multiple hazard scenarios, it's going to take that into account as well. So, or multiple initiating events. So that's pretty nice calculation it does there. The other thing I want to highlight is that it's pulling in your required RRF from select. So I bumped that guy up there, but it is pulling in the required RRF from select and from the LOPA in this case, because I did that calculation in the LOPA. As you can see, the rest of this is blank. The SRS module is really a template that is going to allow you to address all of the different requirements that IEC 61511 wants you to document in your safety requirement specification. If you've ever opened the standard and read all of the bullet points of the different requirements that the design team is going to need to know from the analysis, it's pretty extensive and it can be an overwhelming task. And so the idea here is that you have a consistent way to write your SRS to address all of the requirements, and you're going to generate a consistent report that can be a clear communication to the design team on how to do the conceptual design. If I move to this SIF that I had already defined, you can see it all filled out. And then I'm going to do this here so you can see the fields a little bit better. On the left-hand side here, we have SIF specific information. So this is specific to my high pressure SIF 601. You can see we just have identification information, functional requirements. You can document here intended legs, and then input output, functional relationship, related interlocks, any special requirements, regulatory requirements. Then, of course, you have your integrity requirements here and your SIF failure requirements. Any common cause failures, sensor failure response for the logic solver final element as well, your startup, restart time, things like that. You can document here your desired proof test intervals, override requirements, any operational requirements, or environmental requirements. So all of those can be documented in the SIF specific requirements. On the right-hand side, there's some information here that addresses the entire safety instrument and system. So the first view you're seeing here is the general info. You can document your purpose and scope here. This is going to be an introduction to your generated SRS report. You can link any standards here that apply. You can add definitions and abbreviations as needed. Then you can use this drop-down to go to the logic solver hardware requirements. In this case, you want to document your systematic failure protection, any logic solver failure requirements, interfaces to other systems, functional requirements, operational requirements, and any environmental extremes. You can add notes here, just a notes field as needed, and you can also add custom data. So if this template does not include fields that you feel you need for your SRS, you can identify those fields in the project configuration and then fill out the information here for your safety instrument and system per project, and that will also be generated in the report. Moving along to application software requirements. Again, the standard has extensive requirements they want you to document for this, and they are listed here. So you have your application program, real-time performance requirements here. You have process variable validation, monitoring functionality. You have any proof test requirements, application program failures, your communication interfaces, any references, notes, or again, custom data that you want to add there. The last thing I want to point out is we have general SIF requirements here. So we talked about SIF specific on the left-hand side, but on the right-hand side, you can basically set defaults. If you have things that are specific to your entire safety instrumented system for each SIF, you can fill them out here and then apply them using the buttons at the top to one SIF at a time or to the entire safety instrumented system at a time. So all of your SIFs at once. So let's say your mission time, you know it's 15 years across your entire safety instrumented system, or at least you intend it to be. Perhaps you have desired proof test intervals that are consistent across the board. maybe your override requirements are consistent, or your environmental requirements, anything like that. And you can simply use this button to apply that as needed. And this is a time saver. So if you know that you want your proof test interval to be 12 months or 6 months for the entire safety instrumented system, you don't want to have to type that into each SIF. So we allow you to use this tool for that. Now, once you get back to the safety, the SIF specific requirements, you can come in here and change it. And this isn't going to affect any other SIF. It's just overwriting that mission time for this SIF. So that's an easy way to make sure that you're not spending too much time filling out the same information SIF after SIF. So I like to think of this as kind of a checklist to make sure that you've addressed everything needed for the SRS to be compliant with IEC 61511. Once you are finished with your safety instrumented system, with your analysis, you can generate this SRS report. It's going to generate in Microsoft Word. And what's really nice about this report is that it's consistent. So not only does it look a lot like the module here, but it's always going to be a consistent report that you can hand off to communicate this information to the design team. So obviously you have your table of contents, that purpose and scope. Here, let me zoom in a little bit so you can see it. That purpose and scope is right up front. We have the standards used, your general project information. You have your general SIS requirements. So again, jumping right into those logic solver hardware requirements and application software requirements. And you can see how this looks a lot like the module. So if you're the person who wrote the safety requirement specification and you're wondering where it shows up in the report, it's probably in a very similar spot as you filled it in the module. And you have your general SIF requirements just as a summary for each SIF. And then we have our SIF specific stuff. So first there's an overall list. It's split up in low demand versus high demand, and it's showing just the SIF tag, the SIF name, and your integrity requirements. So your target SIL and your target risk reduction factor. And then it jumps into all the detail for each SIF, so your SIF specific information. And like I said, it's nice that it looks a lot like the module, but it's also nice that it's a consistent report. So if you're the one on the design team receiving this, you know exactly where to find the information you're looking for, because it's always going to generate just like this. And so that is the SRS in a nutshell. And that closes out the analysis portion of the safety lifecycle and how we would do this in exSILentia. So going back to the slides, we are going to do a part 2 that addresses the design and implementation, as well as the O&M phase of the safety lifecycle. So the next webinar, part 2, is going to be June 6th. It's scheduled for June 6th, so please tune in then. And we also want to, if you want to know more, we want to model your SIFs in Silver. So if you have any specific questions, we're always using our own sort of sample problems. We want to know if there are any SIFs that you have that you're unsure how to model them in Silver. We want to collect all your questions and we'll model them live in another webinar, and that'll be on June 13th. As always, we have training. We have a SIL verification course with exSILentia in Houston next week. And then we have also our FSC 100 a few times in Lake Charles in June and in Chicago in July. We have our Automation Cybersecurity Introduction to IEC 62443 in the Philadelphia Navy Yard on June 11th. applying IEC 61511 to burner management systems in June. You can see all the different things we have here. This is obviously a list for North America for this summer, but if you want to take a look at our complete list, go to exida.com/training. We also have online courses. These are self-paced courses. It'll give you access to the course for 60 days. If it's a software course, it'll give you access to the software, and you can take it on your own time. So obviously FSC 101 and 102 are really popular, an overview of functional safety, analysis, design, and operation as it relates to IEC 61511. We also have one as it relates to IEC 61508, FSC 211. We have that same SIL verification with exSILentia course online, FSC 244. We have fundamentals of alarm management for the practitioner. This is new online. And then coming soon, we have LOPA, layer of protection analysis with exSILentia. So that's been recorded and it should be available soon. If you're interested in these, go to exida.com/training/online. And then finally, you can find us on social media, but you can also email us at academy@exida.com. And please let us know if you have any questions on our webinars, or if you have webinar topics you'd like us to cover. We like these to be a learning experience. We want them to be useful for you. So if you have any burning questions, let us know and maybe we'll make a webinar out of it. And that's it. You will receive a recording. You'll receive a copy of these slides. If you have any questions for me, please email me at khildenbrandt@exida.com. If you've asked any questions during the webinar, I can also address those. And thank you for tuning in. Take care.